and good morning. Now I want to go back a little bit from the beginning. You know, astronomy is different from the other experimental sciences in the sense it's a passive science. We cannot go and do any experiment, except to the solar system. So we rely on remote techniques, and those techniques in general can be broken down into photometry, which is a measurement of brightness, imaging, that's mean taking pictures, and then spectroscopy. Now the most important is spectroscopy because it allows us to determine the conditions of the matter that we are studying and also infer the physical conditions of the environment. Okay. Now, and of course, spectroscopy took off slightly more than 100 years ago after the development of atomic physics. Okay. So of course nowadays we extended the techniques beyond the optical to the ultraviolet, X-ray, radio, and so on. Now we are talking about the only available thing to us is the electromagnetic radiation. So we are inferring the structure of the universe because of interaction between light and matter. And there are only three ways, either through absorption, through scattering, or reflection, or emission. Now, emission is very interesting. Of course, we are already familiar with it. Most of the stars emit, and to most people, the universe consists of mostly stars. And then we also have stuff between the stars, and that's we call it interstellar medium, and that also is not empty. And we have abilities because of our knowledge of quantum physics, quantum chemistry, to study these materials. Now, states of matter. Okay, so we have ionic matter. One or more electrons are removed from an atom. A neutral atom, molecules that consist of 2, 3, or more atoms in a system, and also solid state. Now, the techniques that we detect them are different, obviously, for each of these states of matter, and things are not trivial. I'm trying to emphasize a couple points, because when we are able to detect something, it means that it first has to be excited. Now, there's the illustration between absorption and emission. Here is just a background of stars, and you have some dark patches, then that is because there are some foreground solid which obscure the background starlight. So we know that we can infer there is something here. In contrast, matter also emit, in this case interstellar matter, they radiate, in this case in the optical, and therefore we can be aware of their presence. Okay. Now, one of the things I'm going to emphasize is that before you see anything, they first have to be excited. And so historically, the first line detected was the line of hydrogen. Now, it turns out hydrogen is not easy, because the first excited state of hydrogen is a 10.2 electron volts, which correspond to very high temperature. So normally it would not be excited by a collisional process. So when you do see a hydrogen line, that means it was excited by something else. Okay, and that something else, the most common situation, is that it is excited by recombination. So a proton recombined with the electron in the process of coming down, that emit photons, and that's why they're called recombination lines. Now, what does it require? It requires a source of photoionization. So that means you have hydrogen there, but if you do not have background source of ultraviolet light, then this hydrogen you will not be able to see. So we have the first time we study the interstellar matter, we are really looking at ionized state of matter, which happen to have some source of ultraviolet radiation nearby. Okay, so it requires diffuse starlight into ultraviolet. So therefore, the ionized component of hydrogen was detected well before neutral hydrogen and also atomic hydrogen. So now, of course, in the infrared, they can be detected. The whole series of the Balmer lines can be seen. The next logical things are the electronic transitions of common elements. Okay. Now, unfortunately, almost all those lines, what we call permitted lines or resonance lines, are in the ultraviolet. So they are not easy to study. Now, the next element is helium. And helium has a triple state and a single state. So when they cross from one to the other, it's called intercombination lines. And these lines are also in the ultraviolet. Okay. So although we are familiar with the structure of atoms about 100 years ago, seeing them is another matter, because most common atoms, their lines, the permitted lines, are in the ultraviolet. Now, so what did we learn? How did we do that? How do we study the universe? It turns out we rely on forbidden lines. Now, these lines are violates the conservation of parity. So some of the brightest optical lines in the universe, for example, the lines of doubly ionized oxygen, which can be seen to a very high redshift galaxies. That the reason they can be seen not on Earth but in space is because the density in space is very low. The process of collisional de-excitation is very slow, therefore allowing the spontaneous emission to take place. So not only oxygen, but many elements also have these similar kind of forbidden lines, or we call collisionally excited lines. Now, since a collisionally excited process is much faster than recombination, so the collisionally excited lines of the heavy elements actually are as competitive as the recombination lines of hydrogen and helium. So it's why they allow us to see the other elements in addition to hydrogen and helium, although they are relying on different kinds of excitation processes. And the good thing is that because it's a collisional excitation, it does not require an ultraviolet source. Okay, so even very low abundance heavy elements can be detected. Okay, so these lines are also seen in the infrared. So just to emphasize that traditionally we are astronomical observations are relying on the observations in the visible, and therefore traditionally our view of the universe is totally biased towards the ionized component of the universe. Okay, now the next thing beyond ions are neutral atoms. Now it turns out neutral atoms are very difficult to see. Okay, so even common elements like carbon or oxygen, to see them, we have to look for the so-called fine structure lines, and they are all in the far infrared. Okay, so until we have capabilities in space, before these lines were detected. Now element carbon has lower ionization potential than hydrogen, and therefore they are not protected by the shielding of the hydrogen atom, and they are actually quite bright. So this is a spectrum or integrated spectrum of the plane of the Milky Way, and you can see the strongest line is singly ionized carbon. Okay, so you look at external galaxies, again, incredible amount of energy is coming out in a single line of ionized carbon. Now this we didn't know before we have the capability of going into the infrared and also going into space to observe. Okay. Now how about highly ionized atomic species? Now when you take away almost all the electrons of an oxygen atom, then it looks like a helium atom, and then you can see both the resonance lines in the combination lines and also the so-called forbidden lines of oxygen. So just to summarize, because of history, because our restrictions to the visible part of the spectrum, the ionized component of the universe was first to be studied. And our perceptions of the universe are dominated by two things: stars, which are quite obvious, they are continuum emitters, and also gaseous nebulae, which emit line emission, mostly, as I say, either due to recombination lines of hydrogen and helium or collisionally excited lines of metals. Now, molecules came much later. So now they can be detected through the rotational or vibrational transitions. And solid state, for example, on Earth, we are familiar with a lot of solids, ice, minerals, rocks. So all these things, the detection or study of these components of the universe came much later. So this I've said before. So until recently, our view of the atomic component universe is biased towards the ionized component. And I'm going to say a little bit at the later part of the talk about the organic aspects of molecules and solids. Now, gas phase molecules in space. Now, I am old enough to remember in the 1960s, prominent astronomers are telling us there can be no molecules in space. And the reason is very good. Density is too low. You can never form molecules because they rely on three-body collisions. They cannot survive because there are a lot of ultraviolet background. Even if you form a molecule, they'll be broken down. So the traditional wisdom in the 1960s were that if you have any molecules, they would be very short-lived radicals. The radicals probably we don't have an example of on Earth. Now, the only people who were against this trend were Swarovski and Charlie Towns. Okay, Charlie Towns, being a laboratory physicist, he was aware that molecules have transitions in the microwave, and at that time the technology were developed enough that we can have receivers or detectors in the microwave. So he was pushing for taking a look in space to see if there can be any molecules. Now, of course, this is all history, starting in the late 1960s with Charlie Towns' group, and there are many searches, and also the significant development of the high-frequency radio detections at 100 gigahertz range of detection of CO in 1970. Now we have over 200 molecules detected in space. So we don't know how they could come into being, but anyway, theoretical predictions are not always reliable, and we have to rely on what we actually observe. Now, how do we observe them? Molecules, there are three ways. Either they rotate. If they rotate, they go from one quantum state to another. They emit a photon mostly in the millimeter or sub-millimeter part of the spectrum. Or they can stretch. Molecules can stretch. In this way, they emit mostly also in the infrared wavelengths, or they can vibrate. They can vibrate in many ways, and when they vibrate, then they emit a photon which has a longer wavelength of the infrared photons. So we now have the capability, partly because of the detectors, and also partly because of having gone to space. Now we have a much more better understanding of the molecular component of the universe. So these are mostly, this is a typical millimeter wave spectrum, and there are so many rotational transitions of molecules that every single part of the spectrum is filled by a line of a certain molecule. And there's no noise in this spectrum. Okay, every feature you see is a line. And there are so many lines, for example, due to methanol or some a common molecule, that they overwhelmed the entire spectrum, that if you want to search for a weaker signal, say of a more complex molecule, it becomes very hard. And that phenomenon is called confusion, line confusion. So now, there are lots of lines in this spectrum, over 1,000 lines. This is not something new, actually. And of course, they are dominated by simple molecules like CO, CS, SO, and so on. I just want to point out that 14% of the lines in this spectrum are not identified. That means there are still a lot of molecular species that we see them in space, but we have no idea what they are. Now, because we are talking about astrobiology, I just want to say that every family of organic molecules that we have studied in the laboratory on Earth have been detected in space. They include hydrocarbons, alcohol, acids, aldehydes, amine, ether, every family. Okay? So they not only have carbon and hydrogen, they also have oxygen, sulfur, nitrogen, etc. And the modern spectrometers are so good that the spectral resolution is over 1 in 10 million. So when you have a few lines, you can be 100% certain what kind of molecule that you are detecting. So there's some interest in trying to look for biologically relevant molecules. For example, acetamide is the largest molecule that we have detected in space. Astronomers detected in space that show a peptide bond. So glycolaldehyde is the first step of forming sugar. So that is some of the building blocks that we hope we'll be able to detect to gain some insight into the biological phenomena. Now, difficulty is that as you get to a molecule of a larger and larger complexity, it has many energy levels. And that means the partition function is very large, and that means all the rotational transitions are diluted, so the lines are very weak. Okay? So you run into the situation that you have many lines, weak lines, and then at the same time in the spectrum, you have to compete with the much stronger lines of common molecules like methanol. Okay. So there are many attempts to look for, so for example, amino acids or even the basis of nucleic acids and so on. And so far, it has not been successful. But I want to say that the failure of detecting them by this rotational transition technique doesn't mean that they are not there, just because we are running into the partition function and line confusion limits. Now, I want to talk about the simplest molecule, molecular hydrogen. Now, we would expect hydrogen being the most common element in the universe, molecular hydrogen should be everywhere. But it's a molecule which is extremely difficult to detect because you have two identical atoms and there are no electrical permitted dipole transitions. So when we say, oh, we detected molecular hydrogen, what the astronomers really mean is that they detected a vibrational rotational transition of molecular hydrogen, which require the molecule to be excited to 2,000 degrees. Okay? So we do have detection of molecular hydrogen, but they are not in an environment that is commonplace in the universe. Now we would like to detect the fundamental rotational transition, which is this line here. It occurs at 28 micron. So that means we have to go to space to detect this line without relying on some special circumstances to have the presence of molecular hydrogen. But even this line required an excitation of 500 degrees. Okay, so if you have a lot of molecular hydrogen and they are in an environment of 10 degrees, you're never going to see them. So now the whole series of vibrational rotational transitions of molecular hydrogen have been seen, but they are all coming from highly excited regions. Now only after the Spitzer telescope that the three lines, the ground state, first excited state, and the second excited transitions of molecular hydrogen have been detected. And that still meaning that you have an environment which have over 500 degrees of temperature in order to collisionally excite the molecular hydrogen molecule. Now oxygen, I mean the third most common element, is also not easy. Okay? First of all, it can be in many forms. The part of the problem with oxygen is that our atmosphere is made up of oxygen as well, and water, and the lines, the molecules in our atmosphere totally absorb any cosmic signal that are coming in from the outside. So we have a lot of problem detecting water. So the lowest transmission is at 557 gigahertz, which of course require high frequency detector, and they have to get above the Earth's atmosphere. Now oxygen is even worse because oxygen is a boson. It has two identical nuclei, and so the lines that we have looked for are either 119 gigahertz lines or these magnetic dipole rotational transitions, and of all the fine structure lines, they are all either magnetic dipole, or, and therefore they are not permitted in the common sense. Now, there are a lot of radicals in the universe because the density in the universe is very low. The radicals probably can last a far longer time than on Earth, and of course there are many radicals that were detected in space before they were studied in the lab. Even simple molecules of hydrogen and carbon, they have lines in the far infrared, and then we also have the capability of detecting them in the not that long ago. HCO plus is a very common molecular ion, but that line remained unidentified for a long time, although because we don't have a counterpart knowledge of it in the laboratory. Now I want to talk about 3 or more atom molecules. And as I said, you detect them either through bending or stretching or some other more complicated movement modes. Okay. So the simplest thing you can have is 3 atom molecules like carbon dioxide, and then you have vibrational bands in the mid-infrared, for example. So this is an illustration of in the near-infrared, for example, what kind of bending modes have been known by laboratory chemists since the 1960s. So we know that if we have the capability of doing spectroscopy in those wavelengths, we're going to be able to detect some of the stretching and bending modes of molecules in the infrared. Now, another solids. We know there are solids in the universe. In the solar system, we have lots of solids. And the techniques of detect them are either through absorption, as shown in the picture at the beginning, or scattering, or emission. So now, with the development of infrared astronomy, we're able to detect solid particles emitting in space. Okay, so this is a very good picture from the Spitzer Space Telescope in the near-infrared. So the colors represent the brightness of emission in the infrared by solid-state particles. Now, I want to talk about the late stages of stellar evolution. That's not only because that's where my research have been, but also because this is the only site that we can directly witness the formation of molecules and solids in a real-time basis. Now, of course, the late stages of stellar evolution has the advantage because they are the stars that the carbon elements were made in the interior by nuclear fusion. They were brought up to the surface through convection. At that time, the star became very large, what we call a very old red giant. The density in the atmosphere, the temperature in the atmosphere is very low, and they can form simple molecules like C2, C3, and Cn. And we also learned they do something very interesting. In the last million years or so of stellar evolution, for a star like our Sun, it began to eject a very strong stellar wind. Now, this wind is 1 billion times stronger than our solar wind that we have at the present time. And in the process, they create a lot of atom molecules and solids
in the stellar wind itself. I just want to illustrate the extent of the phenomenon. This is a very old red giant that we discovered. This is 1 micron. This is the actually observed stellar spectrum. So this object has no optical counterpart whatsoever. So if we are restricted to the optical, we will never find this object. So this is the inferred photospheric emission. And actually, the star ejects so much stuff, so much solid, that absorb all the stellar optical light and convert everything into infrared. And that's what we are seeing. Okay, so this object shows the extent of the mass loss or stellar wind process. You can totally remove the entire envelope content of the star in a matter of a couple hundred thousand years. Now, with the development of millimeter wave spectroscopy, we can take a look at these stars, and we started doing that in the 1980s. And now over 80 molecules have been detected. They include inorganics, organics, chains, like cyanopolyions or rings and so on. So there are many of the interstellar molecules are represented in these detections. Now, the interesting thing is that because the environment is limited by the dynamical age, the stellar wind has a lifetime or ejection lifetime of about 10,000 years. So we know every molecule that we detect were manufactured in the stellar wind within these short time scales. Okay? So I say that they are very prolific molecular factories. Now, after this stage, they become something called planetary nebulae, which are very pretty objects. Oh, I'm sorry, I jumped ahead of myself. Not only molecules, they also make solids. Now, these are minerals, and they are very, their spectra are well known. So, for example, amorphous silicate, they have Si silicon oxygen stretching mode at 9.7 micron. They have a bending mode at 18 micron, and they can be detected by infrared spectroscopy. Okay? Not only silicon amorphous silicates were detected, silicon carbide is very common. Also, various kind of refractory oxide like corundum, spinel. So a lot of what we call minerals that we are familiar on Earth are being manufactured by these old stars in their stellar wind. Now, the formation of the solid state particle condense directly from the gas phase in the stellar wind. Now, it's not a trivial process, but because when we talk about the density of the stellar wind, they are lower than any vacuum we can produce in a laboratory on Earth. So we are talking a process that laboratory chemists are totally unfamiliar with, because in our terrestrial environment, we cannot reproduce this kind of condensation process. Okay, I want to talk more about organics. Now, of course, before the 19th century, organic matter were considered to be sacred because they were extracted from living organisms. So from living organisms, we can extract from our cells certain molecules which are different from the molecules that you see in rocks, in sand, and so on. And what are different? They are supposed to have something special called vitality. Okay, that is what makes the difference between living and non-living. And now, until the mid-19th century, laboratory chemists were able to artificially synthesize these organic compounds by inorganic means. So we don't need a living person to produce urea. Actually, you can make it in the lab, and the same for amino acids, nuclear bases, and so on. So today, when we talk about organic molecules, we don't associate it
with it necessarily with life. We just say that these are a collection of molecules primarily made up of hydrogen and carbon, but with some other elements thrown in, like oxygen, nitrogen, phosphorus, or whatever. If we look at the distribution of organics on Earth, the first thing you think of is the biosphere. But the biosphere actually is a very small amount of the total amount of organics. A lot more organics are found in the fossil fuels, which of course we know are the remnants of living things in the past. It consists of petroleum, coal, natural gas, and so on. But actually the largest reservoir is in the form of kerogen, which is a complex organic substance found mostly in sedimentary rocks. Now kerogen, according to geologists, are also remnants of past life, but they are precursors of the fossil fuels like petroleum and coal. Now the question is that are there organic matter in the universe? We know there are organic matter on Earth, and they are all the results of life. Now, there are people like Fred Hoyle, who in the 1970s says that the universe is filled of organics, but of course no one believed him, and he kind of being ridiculed for having written about such things. But well, today our perceptions are very different. I'm going to say a little bit about the fact that organics or complex organics are everywhere in our universe today. It started in the late 1960s. A group of graduate students from University of Minnesota and University of California, San Diego, they have access to an infrared spectrometer. They flew on the NASA Kuiper Airborne Observatory. They took a look at some planetary nebulae. Now at that time, people were saying that, well, you're going to see some atomic lines because we know that common elements have forbidden lines or fine structure lines in the infrared. So, but what they found, no one expected. There were a series of very strong lines, and that astronomers have never seen before. The brightest one has 3.3, 6.2, 7.6, 8.6, and 11.3 microns. So right after the discovery, there were two papers in Nature, one by Roger Neck and another by Julian Williams. They both say that the 3.3 micron line, or band, because it's much wider than an atomic and molecular line, is due to the CX stretch of aromatic organics. Okay, well, I counted. In 40 years after those two Nature papers, they got total about 20 citations. Okay, no one thought organics could exist in space. But now we see the same features we call unidentified infrared emission features all the way to distant galaxies. Okay, so you can go to redshift of 2, which means 10 billion years ago. So we know that 10 billion years ago, the universe are already making organics. Now, if you look at the amount of light or energy coming out, it can be up to 20% of total luminosity of a galaxy. Not everyone. Some galaxies can come out from those bands. So this is M82. So the spectrum is identical to those of the planetary nebula NGC 727 when it was first detected. So it's a long story, but I just say in summary, there are strong UIE bands at 3.3, 6.2, 7.7, 8.6, 9.3 microns. There are also later, part of it was discovered by us, that there are aliphatic features at 3.4 and 6.9, but there are also features that are not yet totally identified at 15.8 and so on. Now most interestingly, all these features, they sit on broad emission plateaus which are about 2-3 microns wide, and then they sit on a very bright strong continuum, which extend all the way from 2-3 micron to millimeter wavelengths. So the three things together actually make the phenomenon. So the key question was the electrochemical structure of the carrier. Now today I don't have time to go through 20-some years of history, but I just want to say that nature is very smart. Okay? By mixing two components, hydrogen and carbon, nature can create very complex hydrocarbons. And here in this triangle, you see that we have two things that we are familiar with in our terrestrial environment. One is diamond, another is graphite. Graphite is a planar two-dimensional structure, and diamond has a tetrahedral structure. Now once you introduce hydrogen into carbon, so you add another corner to this triangle, then you can make all kinds of what we call amorphous carbonaceous hydrocarbons. Now, many people over the world have been trying to do that. In the laboratory, they try to simulate the creation of these amorphous hydrocarbons, and the techniques are almost all similar. Okay, so what they do, they put a bag of gas phase hydrocarbons like acetylene or methane or whatever in the bag, and they bombard it with energy, either by laser, ultraviolet, radio waves, or heating them up. Just put some energy in there, and then you let the content evaporate, and you collect the substance on some substrate. Okay, and then you take the stuff out of the substrate, you analyze them. It turns out, no matter what technique you use, the results are always similar. Okay? You have a collection of amorphous hydrocarbons which consists of islands of aromatic rings with chains of different, aliphatic chains of different lengths and orientations. So you take a spectrum. Okay, so this is one of those I mean, this is by no means unique. I mean, you do an experiment, you take a spectrum, so you have this kind of spectrum. And this below is a spectrum of planetary nebulae. That you can see that there are some resemblances. Now, there's another technique by a French group, and again, you can see some qualitative resemblance to the astronomical structure. So in 2011, we published a paper. We proposed that the carrier of these features is mixed aromatic aliphatic organic nanoparticles, or muon, and the characteristic is that they have rings. They have rings here and there. All these rings are connected by aromatic aliphatic or olefinic bonds, and they have other impurities like oxygen, nitrogen, and sulfur, because nature is not a control laboratory. I mean, when you make something, you probably have some impurities in it. So, so this one, I didn't have a number here, probably has about 100 some carbon atoms, and it's about 1 nanometers in size. Okay. So in the meantime, that there are other people who have do absorption spectroscopy. Now, absorption spectroscopy has the advantage that it does not require any interpretation, because the strings of the line that you see is just the product of the column density multiplied by the oscillator strength. So this is the 3.4 micron CX stretch, 4 lines, either due to symmetric or anti-symmetric stretch, which we first discovered in the protoplanetary nebulae. And these are clearly in a absorption line of sight. And you look towards the galactic center, so the author's conclusion is that at least 15% of all the elemental carbon are tied up in aliphatic organics. Okay, now, at the same time, the planetary science community have been very busy. They know that there are lots of organics in the solar system. They know that there are they're in comets, in asteroids, and so on. Now, of course, they go back to the beginning of spectroscopy, so we know that, all the planetary satellites or planets have things like acetylene, methane, and so on. So this is nothing unusual. Many of the same gas phase organic molecules are seen in our solar system by remote spectroscopy. So, in meteoroids, we know that they are complex organics. Current techniques which allow laboratory scientists to analyze the components of the meteoroids. Basically, all known organics and more are found in meteoroids. For example, our body only used 20 amino acids, but in meteoroid they have over 100. We only use 5 nuclear bases to form DNA and RNA, but they have far more. Okay? So all biological relevant organic compounds are pleasant and more. No, our body amino acids are all left-handed, but in a meteoroid they are both right and left-handed. So they have unusual nuclear bases. So nature, being able to make organics abiologically without any interference from living things, and they have generated a much larger reservoir of ingredients, and on Earth we only choose to use a small fraction of them. So in carbonaceous chondrite there is a component which is not soluble, and if you look at the content, they make up of islands of aromatic rings, and if you analyze the elemental abundance, they can be taken in the ratio of carbon 100, hydrogen 46, or nitrogen, or whatever. So comets, we know that the tails of comets have a lot of organics, and even the nuclei of comets. Now we have Rosetta, and we can fly to or stardust. We can fly to and collect the stuff and analyze them in the planetary particles, and fly airplanes to collect them and analyze in the lab. This 3.4 micron component is the same as what we see in protoplanetary nebulae. We know that Titan is covered with hydrocarbons. The amount of hydrocarbons in Titan is more than the gas and oil reserve on Earth. Oops, sorry. So in the past, people think the solar system will primarily consists of ice and minerals, but actually now that we know there are lots of organics, and there is also common to believe that everything that we have in the solar system were made 4.6 billion years ago. There were new things that had coming from outside and could have survived the early solar system, except after the discovery of so-called pre-solar grains. Now, these pre-solar grains have isotopic signatures which are not like the sun, but totally agreement with old red giant stars. So this stuff, either is silicon carbide or corundum or diamond, they were made in old stars. They travel across the Milky Way galaxy. They were deposited into the early solar system, and they were delivered to Earth. Okay? So we do have a connection with stars because they are almost definitely of stellar origin. Oh, we also know that stuff fall on Earth. Yes, if you wonder that. Now, the question is, are there any primordial hydrocarbons on Earth? Now, in the book, The Deep Hot Biosphere, Thomas Gold proposed that. Of course, he was never taken seriously by the scientific community, and probably got it for a good reason, because Gold proposed that at that time, methane was detected astronomically, so he said, well, the early solar system had a lot of stellar or interstellar methane. They were, when the Earth was formed, they trapped probably a lot of methane, and from chemical reactions deep in the Earth's atmosphere, this methane became petroleum or
coal and so on. And that's probably not a reasonable scenario. But, well, of course, I mean, we have a very strong link between petroleum and life. So as far as the geologist's point of view, that all the oil that we have are biological in origin. But we do know that not 100%, there's a little bit not biological because we have methane and hydrothermal vents. All right, okay, but they are not significant. Now, however, if the primordial hydrocarbon is not a gas phase methane, but some macromolecular compound like ammonia, then the chance of survival would be much, much higher, because these things are extremely difficult to break up. Now, once they are collected in the inside of the Earth, over time, under thermal pressure and temperature, they can gradually degrade it into coal and oil. So we have to consider the possibility whether there are such things, because all our knowledge of the fossil fuels are on the surface of the Earth. Now, I think I have run out of time, right? So I'm going to omit the rest of the slides, except to say that we still have a lot of extremely well documented unsolved mystery in astronomy. I'm not going to go into the details, I'm just going to list them. Okay? The first is diffuse interstellar bands. There are over 600 bands, extremely high signal to noise. They have been collected over the period of 100 years. Of the 600 bands, only 2 maybe have been identified. Those are due to ionized fluorine. The rest are totally unidentified. So I think these are mostly due to electronic transitions of gas phase molecules, gas phase organic molecules that we don't know. There's the 2200 angstrom feature, which is seen all throughout the universe. The extended red emission, this is an optical phenomenon. They are seen in circumstellar of stars, in the stellar medium, in galaxies, in quasars. So they are still a lot of things we don't understand. Now, the fact that you don't hear much about them from astronomers is not because they don't exist, not because they have been solved, it's just because they have been ignored. Okay, because the people don't want to work on something they can't publish the paper next week. That's that. So, optical lines that you see by looking at some hot stars as background, and you take the spectrum and they are absorptionized. There are over 600 of those lines, and they can be seen over a line of sight over multiple number of stars, because they is an interstellar phenomenon. They are also seen in galaxies, in quasars, and when I put down none of the bands identified the last year, there were 2 suggestions of 2 lines that are due to ionized fluorine. Okay, so well, maybe 2 out of 600 some. So according to Ted Snow, these, whatever the carrier is, these represent the largest reservoir of organic material in our own galaxy. Our galaxy definitely has a lot of organics, not in between of stars, because these lines are very strong, and because they are absorption phenomenon, there are no question about interpretation, because you can infer the abundance by just looking at the column density. And you have a lot of organics. The thing is that we don't know what kind of organics. Okay? So these show you a typical spectrum. All we know is that they are probably electronic transitions of gas phase molecule. The only carbon probably has the abundance to be able to form such a large number of these carriers, and many gas phase radicals have been explored in the laboratory as possible carriers of these bands. Now, of course, the difficulty is that if they are radical, then it's very difficult to make them in the lab. And of course, after you make them, you have to make them live in long enough to do spectroscopy. So as I say, the only one that has shown a match of 2 bands are ionized C60. Okay. So, well, this is only my hypothesis, because we are promoting the idea of complex macromolecular organics. So I was saying that could they be breakdown products of MONCs? Okay. Now the 2200 angstrom feature, discovered in 1965 by ultraviolet spectroscopy. They are based on the so-called extinction curve. The extinction curve is that when you look to a star, you take their spectrum over a wide range of wavelengths, and they deviate from the stellar spectrum because of absorption by solid-state particles. So you can explain a lot of the difference in the extinction curve, or the absorption, by intervening solid-state particles in the stellar medium, for example, due to amorphous silicase. But there is one feature which is very strong, very well documented, has a very well fixed peak, and the profile not identified. So because this feature is so strong, it has to be made up of a abundant element. But what can be this element? Most likely carbon. Okay, so these are some of the actual spectrum of stars, and you can see that, you know, there's supposedly the stellar spectrum be something like that, stellar atmosphere, and then you have this huge dip in here, which is due to absorption of an unknown substance. It peaks at 5.7 electron volts. Now it turns out that many of the semiconductors, or carbon-based semiconductors, have a band gap around 5 electron volts. So it's consistent, it being some kind of amorphous organic solid. Okay. So now also interestingly, in the solar system, for example, when we collect in the planetary dust particle, you also can see this feature. So this feature, whatever the carrier, is not only exists in the stellar medium, in galaxies, in quasars, but they also are embedded in the planetary dust particle of the solar system. So there may be some connection between interstellar, and solar system solid. The 2200 angstrom feature is an example. So in 1989, we discovered by accident a very strong feature at 21 micron due to in protoplanetary nebulae. And these stars are very carbon rich, so we assume that they are due to a carbonaceous compound. So you can see by yourself, just on this spectral energy distribution, that a lot of energy is coming out from there. So you take the higher spectral resolution observations, and then you have a very consistent peak profile at 20.1 micron. They have a very asymmetric profile, again very consistent. So there are no sign of any substructure. Now see, because the width here is 1, 2, 3 micron, or 3 or 4 micron. So it's very wide, so it's not due to any molecular species. So, but most likely due to some kind of a solid. So many theories have been proposed on the origin of the 21 micron feature. I just say that none of them have been demonstrated to be totally successful. There is also a 30 micron feature, also found in planetary nebulae and stars and so on. And about 20% of the total energy of the star is emitted in this feature. Okay, so this is a star that shows both the 21 micron feature and the 30 micron feature. And these things are the UIE features I was talking about. So this is 3.3, 7.7, this is 11.3. So all these are unexplained phenomena. Now, extended red emission. Now this is an optical phenomenon, and it's very broad, 80 nanometers. So it's primarily in the red. That's why it's called extended red emission. So the hypothesis is that this is due to some semiconductor. It's a photoluminescence phenomenon. They are
being heated by ultraviolet photon. So in the solid, they undergo photoluminescence and then create this continuum optical light. So now the thing is that these processes are extremely efficient. Okay, they are very efficient in terms of converting the ultraviolet light into optical light. Now, so this is the band gap, and so you say, what's the carrier? Okay, again, because there's so much of it in the Milky Way galaxy, again, it has to be due to some most likely carbonaceous compound, some carbonaceous semiconductor, and no one has yet found a solid-state semiconductor that has explained this photoluminescence phenomenon. 4% of the energy absorbed by the total interstellar solid-state component, less than 0.5 micron, is emitted in the form of the ERE. So it really is a very common phenomenon. So most likely some kind of a nanoparticle, and because physicists have not studied semiconductors in the nanometer region that much, so we probably not found the counterpart in the laboratory. So I just think, in spite of the fact that we have a couple hundred years of astronomy, I want to emphasize that we don't know everything because of the limitations of our techniques. Okay, we do whatever we can with the techniques available, but even simple things like hydrogen, molecular hydrogen, we have not have a good knowledge. When people tell you, oh, there are so much gas in a certain galaxy, what they are telling you is that they're inferring that number from carbon dioxide, okay, because CO is easy to see, and they say, well, I assume the CO to H2 ratio is such and such, therefore there's so much mass in that galaxy. Well, maybe they're right, but I want to see direct measurement of the abundance of molecular hydrogen. Okay? The problem is that any active molecule or solid, they have to be excited to be seen, and that is the problem. Okay? So astronomers are not all powerful. We have to rely on suitable circumstances, and if we don't have them, we don't have a clue what is out there. So so now we detected 200 interstellar gas phase molecules. Many of them are organic. They're mostly detected through the millimeter and submillimeter and infrared spectroscopic techniques. We believe that we now have evidence for the existence of very complex organic compounds of aromatic aliphatic structures. They are seen in stars, they are seen in diffuse in the stellar medium, they are seen in galaxies, and they are seen in the solar system. To me, the interesting thing is that these organic solids can be made over a very short time scale, hundreds or at most thousands of years, in a very low density environment. And because we can see them forming, we have done spectroscopic survey of stars in the various stages of evolution. We can follow the gas phase chemistry, we can follow the formation of various signatures of organics. Now, all these organics are nothing to do but with biology. Okay, so they are all abiotic. Now, how do we know that? For example, in the case of circumstellar environment, we can see them forming. For example, when in a circumstellar envelope, we first see the acetylene. Acetylene is a linear molecule. Then you put three acetylene molecules together, you bend it into benzene, which is seen in the Polyplanetary Nebula. Once you have the first ring, there are probably some junk attached to it. You begin to see the methyl and methylene groups attaching to the rings. So we can see them being formed from the bottom up. And also, even in the solar system, in meteoroids, you look at the abundance of all the organics, the larger abundant organics all have fewer carbon atoms. So they are building from the bottom up, not a break-up product of life. Okay. Now I hear all kind of things from the extrasolar planet community saying, oh, biomarker, whatever. I mean, oh, they detect methane is a biomarker. I mean, methane is everywhere. I mean, we have methane in Jupiter, in Uranus. I mean, so it doesn't mean there is life on Jupiter, right? Okay. And we have a number of unexplained phenomena which are everywhere in our universe. And after 50 to 100 years, we have no explanations to them. Okay? As I say, really, we have to put more effort because it's obviously important because they are due to unknown organic carriers. Okay? Or these kind of carriers we haven't learned from laboratory chemistry. Now we have complex organics in comets, asteroids, planetary dust particles, planetary atmospheres. It's possible that some of those organics are of interstellar origin. So because we have the pre-solar grains, we have seen the possibility of a stellar ejected solid travel through the Milky Way galaxies and deposit into the solar system and preserve to this day. Okay, so why not organics? If they were preserved, the question is that did the Earth receive any external stellar organics? Right? So here are some references. If you are interested, you're welcome to read those papers. Maybe I'll just leave the time for discussion.
This is quite perfect.
Yeah, thanks.